Greetings, my wonderful students. I, Dr. Jyoti Vaibhavi, welcome you to second lecture video of microcirculation. So these are the specific learning objectives. Okay, it's very important. So please go through them properly. Then in today's lecture, we are going to cover all these topics one by one. We are going to study about the Starling forces, some terminologies. We are going to understand a little bit concept about the interstitial fluid pressure, and finally we will learn how to analyze Starling forces. So this lecture will be useless if I forget to mention about this famous British physiologist. Who is he? Yes, he's Ernest Henry Starling. Okay, so he has contributed many fundamental ideas to the medical field. So some of the significant contributions are like this: Starling forces, which we'll be studying today, and Frank Starling's law. As we all know, we have studied extensively in the cardiology classes, in cardiovascular physiology classes, about the Frank Starling's law, Starling curves, how important it is to know about it, to learn about the cardiovascular system. Also, he and his brother-in-law, they both together discovered the hormone secretin. Okay, and the term hormone was coined by Starling for the very first time. Also, the evidence of vasopressin was proved by Starling, and he also has written a Starling physiology textbook, which actually went through 20 editions. So, after paying homage to this great person, let's see what are Starling forces. So, Starling forces are the four primary forces which determines whether fluid should come out of the capillaries or should go back into the capillaries. So the Starling forces are capillary hydrostatic pressure, capillary plasma colloid osmotic pressure, interstitial fluid hydrostatic pressure, interstitial fluid colloid osmotic pressure. The capillary pressures are the major pressures, whereas the interstitial pressures are the minor pressures. We'll learn each one of them one by one. So coming to the capillary hydrostatic pressure. So let's go back to our heart. So when left ventricle of the heart is pumping, yeah, it is pumping the blood with a pressure into the whole systemic circulation of the body, isn't it? This we usually refer as blood pressure. So blood pressure is nothing but the hydrostatic pressure. By the time the blood comes to the capillaries, the pressure falls. Yeah, it's not as much as that when it was at the left ventricle. But this pressure is good enough to force the fluid and its dissolved substances through the capillary pores into the interstitial spaces. So it's basically an outward force. So when you measure it in the skeletal muscle and gut, by indirect method, that is isogravimetric method, it was around 17 millimeter. Directly through micropipette method, it was around 25 millimeter. So capillary hydrostatic pressure is nothing but outward pressure. Okay, and coming to capillary plasma colloid osmotic pressure, one more pressure which is present in the capillary. These are the molecules. There are molecules, there are ions or plasma proteins that fail to pass through the pores of semi-permeable membrane. Plasma contains some molecules, some proteins. They actually cannot cross through this membrane, and hence, because they cannot cross, you remember osmosis. Whenever there's an impermeable solute present, it exerts a osmotic pressure. There is osmosis. It sucks or draws the fluid towards itself, towards the solute containing compartment. Same thing here. Plasma proteins which are present here, due to the osmotic pressure, they drag the fluid. Okay, they drag the fluid inwards towards them, or hold the fluid whatever is present in the capillary towards themselves. So it's basically a inward force. Okay, when they measured it, it was 28 millimeter of mercury. Then coming to the interstitial pressures. Interstitial fluid colloid osmotic pressure. So whatever the fluid constituents are present in the plasma, the same constituents are present in the interstitium. They are separated by capillary membrane. The only difference is the plasma contains big protein molecules like albumin, globulin, which cannot cross through the capillary membrane into the interstitial fluid. Now, so sometimes small amount of plasma proteins do leak through these pores into the interstitial spaces. Sometimes by these pores or sometimes by transcytosis. The small proteins which come here into the interstitium, these proteins exert osmotic pressure, or they also there is also osmosis because of this proteins here, and they drag the fluid towards themselves. So it is a basically outward force which is sucking the fluid towards the interstitium. So compared to these pressures, this is small, minor, but it is a interstitial fluid colloid osmotic pressure is a outward force, means it is making the fluid come outside the capillary. Okay, so it is around 8 millimeter mercury. So coming to the interstitial fluid hydrostatic pressure. This is a fluid, so it has to force the fluid inward through the capillary membrane. This is what we all know. We all think because it is a fluid, it should go inside. Okay, so there's a tricky situation here. Yes, it goes inside whenever the interstitial fluid pressure is positive. Sometimes when it is negative, it comes outside. Okay, but one thing I want to tell you here is that, so what do you think? The entire tissues of the human body, when you take interstitial fluid, is positive or negative, or both? Just think, keep thinking. So interstitial fluid pressure, again, if I have to state, whenever it is positive, it acts as an inward force and it forces the fluid to go inside the capillary. When the interstitial fluid hydrostatic pressure is negative, it forces the fluid to come outside. Yeah. Now, it tends to force fluid in either way. When you measure the tissues of most of the tissues of the human body, the interstitium, everywhere except for encapsulated organs like kidney and brain, most of the tissues, the interstitial fluid pressure is negative. Yes, it is negative. So it is a majorly acts as a outward force. So the outward forces which helps, outward forces are mainly, it helps in filtration. So capillary, interstitial fluid, colloid osmotic pressure, all these are outward forces. The only inward pressure is plasma colloid osmotic pressure. Okay, so now as a good student, you should ask me, why ma'am, why it is negative? It is a fluid in there. It's so much of fluid, and why it is negative? Why is not positive? This is the question you should ask me. So for the answering that question, let me first teach you some basics about interstitium, or let's recall what is interstitium and what is interstitial fluid, right? So you remember this picture we had learnt in body fluid compartment? Yeah. If you take a 70 kg man, 60% of his body weight is made up of body fluid, body water. So that is around 42 liters. If you take this 42 liters, in that 60%, 40% is present inside the cells. Whatever the fluid is there inside the cell, it is called as intracellular fluid here. Whatever is there outside the cell, everything in the interstitium, in the plasma, in the blood, everything which is outside the cells are called as extracellular fluid. So extracellular fluid is either in the interstitium or in the plasma. Okay, So 20% of the body weight, that is 14 liters, is present in the extracellular fluid and 28 liters here. If you take this 14 liters, to 3/4 of the ECF, that is 3/4 of 14 liters, is around 10.5 liters to 11 liters is present in the interstitial fluid, whereas only 3 to 3.5 liters is present in the plasma. So now 28 liters is present in the entire body in the intracellular only. 11 liters here, 3 liters in the plasma. So with this information, you should know that interstitial fluid, there is 11 liters in all over the body. Okay, this picture I have put so that you remember what is there inside the cell, what is there outside the cell, how is plasma and interstitial fluid same or different. So this is intracellular, that is inside the cell. So as we know, potassium is the major intracellular ion, whereas sodium is the extracellular ion. So you can see sodium is more outside the cell, inside is very less, and potassium is more here, it's very less here. And the difference thing you have to remember, in intracellular there is protein, in plasma there is protein, that is in the capillary there is protein, but in the interstitium there is no protein. Okay, this is the major difference between plasma and interstitium. Other than that, everything is same in the between the capillary and the interstitium. The only difference is this proteins. Okay, so with this basic information, we'll see the structure of the interstitium. So as I said earlier, about 1/6 of the total volume of body consists of interstitial space. This picture, take a look. This is the capillary. These are the cells. Yeah. In between these two cells, there is interstitium. So, what is this interstitium made up of? It is mainly made up of two solid structure. That is the collagen fibers. Can you see this collagen fibers? And this small purple things, fiber things, these are proteoglycan filaments. These collagen fiber bundles extend long distances in the interstitium, okay, and they are extremely long. They are strong, they are long, and that's why they give the tensile strength to the tissue. The tissue gets this strength from these collagen fiber bundles, okay. Then there is this proteoglycan filaments. Okay, you can see them. They're very thin. You cannot see them. Even in under electronic microscope, you cannot see them. They're that thin. Okay, they're mainly made up of hyaluronic acid. Okay, even though they're very thin, they play a very important role. They form a mat, a fine reticular filaments, like a mesh. They make like a mesh. That's why they're called as brush pipe. These proteoglycan filaments, even though they are thin, they play a very important role. They're called as a mesh, brush pipe. Okay. What's the main use of this proteoglycan? Collagen provides strength, tensile strength, whereas proteoglycan filaments, they prevent fluid from flowing too easily through the tissue spaces. Fluid does not just run around like that. Imagine a person without proteoglycan filaments. If proteoglycan filaments are not there, if a person stands up, okay, the interstitial fluid would run from upper body to lower body like that. Just like that. Because proteoglycan filaments are there, the fluids just stays there. Okay, so it holds the fluids in that form. It doesn't allow fluid to easily run through. Okay, this is how interstitium is laced around. And gel in the interstitium, yes, the fluid in the interstitium, whatever the fluid is coming here, is coming from the capillary, isn't it? Okay, all the constituents is derived by filtration and diffusion from capillary to interstitium. The only major difference between the interstitium and plasma, as we have discussed, is the proteins. Yeah. Where are this fluid present? There is this, what is this? Collagen fibers, there's proteoglycan filaments. Where are these present? In between this purple, can you see some fluid here? This pink color. Yeah. So fluid is entrapped in between the proteoglycan filaments. Okay, fluid and proteoglycan filaments together, they form like gel-like structure. It's not like fluid form. The fluid is like a gel. When I tell interstitial fluid, it's not like in between the 100 trillion cells the fluid is running. It is like a gel. It gives that tissue strength. Okay. And free fluid in the interstitium. Where is this free fluid? Why is it called as free fluid? So you can see this. This is a capillary. These are collagen fibers. These are proteoglycans, and there are fluid here. But if you can see, there are these small purple things. Can you see? These are nothing but fluid filled vesicles. Okay. Fluid which is free from proteoglycans are called as free fluid. Also, they are easy to run around. The fluid which is present here with the proteoglycans are gel-like, but the fluid in the vesicles, and there are also spaces called as rivulets of free fluid. Here the fluid is like free flowing. So whenever there is extra fluid coming into the interstitium other than 11 liters, if for example there is 15 liters coming into the interstitium, these rivulets and these vesicles, they are enormously filled with free fluids, and that's when the edema happens. Okay, so when I say interstitium, it's mainly here in between the cells. They are free, they are gel like. There is this collagen and proteoglycan. Okay, this is what you have to remember. Now coming back to the question, so why interstitial fluid is negative? Why when they measured it came as negative? Okay, this was our question. Most of the tissues are negative. Why? Why? So you remember this picture? It's again illustrated diagram. It is just showing that from arterial end the fluid is filtered and it is utilized by these tissues, and the extra fluid whatever is there is filtered, reabsorbed back into the venous end. Right. So sometimes what happens, some proteins, some things come into the circulation which cannot be reabsorbed. So who is taking that back to the circulation? Yes, it is your lymphatics. The lymphatic system acts like a scavenger system, right? That removes excess fluid, excess proteins, excess debris, excess which we don't want is removed by the lymphatics. Normally, when fluid enters the terminal lymphatics, the lymph vessels here, okay, goes and again goes to the thoracic duct and to the right atrium. Again, all the fluid is going back here. This lymphatics here, you please concentrate here. Yeah, attention. The terminal lymphatic capillaries here, the lymph vessels, automatically contract for a few seconds. Okay, they contract for a few seconds and pump the fluid through the lymphatic capillaries. Okay, they automatically contract and pump. So when they are contracting and pumping, this overall process of contracting and pumping creates a negative pressure here in the interstitium. So interstitial pressure is negative because of the pumping action of the lymphatics. Did you get it? How amazing. There is lymphatics which is not only helping us remove the fluid, but also it is creating a negative pressure in the interstitium. So what's the reason? Pumping of the lymphatic system is the cause of the negative interstitial fluid pressure. So somebody asks you, so why the interstitial fluid pressure is negative? You have to answer that it is because of the lymphatic system pumping. So now that we know that interstitial fluid pressure is negative all over the body, we have to know the advantages of it. Is it really advantageous or not advantage? Obviously, when it is throughout our body, it should be advantage. So let's see what happens. So because Interstitial fluid hydrostatic pressure in the most loose subcutaneous tissues of the body, slightly less than the atmospheric pressure. It's around minus 3 millimeter of mercury. What is it? It is around minus 3. This slight section in the tissues, so this, because it is negative, it creates a suction pressure. Okay, slight section which helps to hold the tissues together. How amazing, isn't it? So because there was negativity, the tissues are held together because of this negative pressure. Also, one more advantage of it is the negative pressure leads to low compliance of the tissue. When I say low compliance, what do you mean by it? So let's look at this picture here. Okay, don't get tensed, it's just a normal picture. X-axis is showing the interstitial free fluid pressure and the y-axis is showing the interstitial fluid volume. So usually it is at minus 3. So if we can draw it, okay, so it's here. Usually it is at minus 3. One second, I'll take the pen. Yeah, here if I can draw it, it is around 12 liters. Normally it is at minus 3. Yeah, when I measure. So what does you mean by low compliance? This is what we have to learn. What is low compliance? So for every millimeter change, so let me change it from minus 3, I'll make it as minus 4. For every millimeter change, the volume change which you can see, I think it's almost same. Yeah, so compliance means for every millimeter change, what is the volume that is getting changed? So if the volume is not changed too much for every millimeter change, it is called as a low compliance. If there is a less volume change for every millimeter change, it is called as low compliance. So we can see here also, instead of minus 3, I'll make it minus 2. So not much change, almost same, right? When it is negative. So if interstitial fluid pressure was positive, let's take like that. Okay, I'll take another color. Okay, so if it was positive, for example 0, if I take 0, so maybe the volume was around 17, okay, 17 liters. Okay, let's change. For each millimeter change, what is the volume change? That's what we are seeing, whether it is low compliant. For 1 millimeter, let's see what is the change. So it was almost 16 here, it became almost 23. Oh, lot of change. For another 1 millimeter, when it was positive, it's almost 29 liter. So you understood? If the interstitial fluid pressure was positive, it would have been a high compliance tissue and it would hold on to a lot of fluid. Because interstitial fluid is negative, it is a low compliant, and that's why there is very less volume change. So how nature is so wonderful. See, it has thought about it, and the negative pressure, it is made the interstitium as a low compliant tissue. Amazing. So if the interstitial fluid for pressure for some reason becomes positive, then it holds on a lot of fluid and it causes to edema. So being negative is actually a safety factor. It is the safety against edema. So nature has made interstitial fluid not to have too much fluid by making it negative and less compliant. Do you understand the advantage? Okay, I hope you understood. So let's summarize. So these are the 4 forces acting. These are called as the Starling forces. Okay, so interstitial fluid pressure being negative. So these are the 3 outward forces and 1 inward force. So next we'll move on to net filtration pressure. So what is this net filtration pressure? So sum of all the Starling forces, which tells us whether there is a filtration or absorption, is called as net filtration pressure. It's actually given by this formula. So P is nothing but the fluid pressures, and pi is nothing but the colloid osmotic pressures. It is given by this. At this stage, I would request you to take your pen and paper, and so that it will be helpful for the upcoming slides. Okay. So it's given by this formula. So when the net filtration pressure is positive, there is a filtration. When it is negative, there is absorption. Okay, nothing much. Then moving on to the rate of fluid filtration and capillary filtration coefficient. Okay, so what is this rate of fluid filtration? It's nothing but net filtration pressure but capillary filtration coefficient times. Okay, so when you multiply Kf by NFP, that is net filtration pressure, we get the rate of fluid filtration. We'll understand whether that particular tissue there is more filtration or less filtration based on this formula. This capillary filtration coefficient, it's actually a measure of the capacity of the capillary membrane, how much it can filter. It usually depends on the number and size of the pores and number of capillaries in which blood is flowing. There are more number of capillaries for each tissue, there is more rate of fluid filtration. If the size of the pores, number of the pores are bigger, obviously there's more rate of fluid filtration. So this is more useful when we talk about glomerular capillary filtration, glomerular filtration in the renal chapter. Now let's move on with basic information about the Starling forces. Let's analyze the Starling forces. Okay, well, let's see how it acts. It's acting on the tissues or acting on the capillaries, how this filtration absorption happens. Okay, let's consider this picture. When you see, there's this arterial end, there's this venous end, and these are capillaries. This is nothing but the microcirculation without the lymphatics. So when you consider, even though capillaries are like one single tissue, the arterial side of the capillaries, they behave like totally different tissue, and venous side, they behave like a different tissue. If I can just take the arterial side has a higher pressure compared to the venous system. They are lesser pressure system, and arteries are more muscular, and they have a smaller lumen compared to venous system. So there are a lot of differences. This is actually two different systems totally combined at the capillaries. So you can just take the arterial system out of this capillary bed. I have just taken out the capillary bed, arterial capillary bed, and here we'll see how the Starling forces are acting. Okay, so when they measured the arterial end through experiment, they found out these values. Okay, so capillary fluid pressure was plus 30, and obviously it is the outward pressure. Plasma colloid osmotic pressure was plus 28 at the arterial end, and interstitial fluid colloid was plus 8, and again it was interstitial hydrostatic pressure was minus, that is minus 3. Because it was minus, it is outward force. Now if I put the formula, if I substitute all the outward forces together, 30, 38, 41 minus 28, so it is around 13 millimeter outward. That is, the fluid is coming outside the capillary. Filtration is happening at the arterial end, right? So let's consider the venous end. As I told, it's totally two different system. To make you understand, I'll just take the venous part out, and we'll see how the Starling forces act here. Okay, if you can remember, the pressures are same. The plasma colloid osmotic pressure is same. This is same at the venous end. This is also same. Only thing which has changed is the capillary hydrostatic pressure. As I told you, the arteries are a high pressure system, whereas venous end, it is a low pressure system. So here the pressure of the capillary hydrostatic pressure has decreased compared to the arterial side. So if I put the formula here, because it is minus, all these are outward forces and this is inward forces. So we'll put the formula here. When you combine the outward forces, it is still less than the inward force. So the answer is -7, or you can say the filtration pressure is inwards, that is reabsorption is happening. Okay. So Starling pointed out more than a century ago that under normal conditions, a state of equilibrium exists in most of the capillaries. That is, amount of fluid filtering outward from the arterial end is exactly same as the reabsorption from the venous end. Okay, this happens in almost all the tissues. Whatever the little extra fluid has come out into the interstitium is drained back by the lymphatics outside. So if you don't just take arterial or venous end, we'll just all over the capillaries across. How does it behave? It behaves like this. So these are the pressures, the net equilibrial pressures. Okay, so when we substitute this for the formula, what are we getting? We are getting 0.3, which is very minute. Okay, the slight imbalance, that is 0.3 millimeter, whatever the little minute pressure, whatever the fluid has come out, which is not able to being absorbed, this 0.3 millimeter is taken away by the excess filtration, is taken away by the lymphatics. So almost equilibrium is managed. So let's summarize what we have learned. We learned what is body fluid compartments, what is interstitial fluid, we learned what are the Starling forces, we learned what is net filtration pressure, we learned what is the rate of capillary fluid filtration, we learned what is capillary fluid filtration coefficient, and very important concept we have studied today was why interstitial fluid pressure is negative and its advantages, and also we learned how to analyze the Starling forces. So this was about today's class. Next class, the whole purpose of studying Starling forces is to understand the imbalance. Whenever there is an imbalance, there is edema and all that. So the next class we will be studying about the abnormal imbalance of the Starling force at the capillary membrane. So thank you all for patient watching.